Hi folks, Chris McClure here. Now we move on to Chapter 5, which marks the first bit of material for the second half of the course, on which we will be tested on the final exam. So we're going to talk and start talking about distributions, in particular probability distributions. We're going to be combining everything that we have learned so far, combining our discussion of descriptive statistics with probability together to make probability distributions. Probability distributions talk about what will probably happen, might happen. Of course, in the world of statistics, we don't know anything for sure except something's going to happen. But the distribution will give us the probability that your what we call a random variable takes on either a particular value or a range of values with a particular or calculated probability. And we can get that information regarding the probability by looking at a graph of the probability distribution function or a table or some sort of mathematical formula, as we shall see. We're going to talk a lot about random variables in this course, and you know what? A random variable is nothing more than just a variable where the output is going to be a probability and the input is going to be some number. Now, there are going to be two different types of random variables and thus two different types of probability distributions. Every random variable has a particular distribution. And anywhere, we're going to be looking at the discrete type and the continuous type of distribution in random variable. We're going to be focusing on the discrete random variable / probability distributions in this chapter 5, and then we'll look at the continuous distribution in a later chapter. The particular distributions that we'll be looking at here in chapter 5 is the binomial and the Poisson probability distributions. Both of them are very important. Here's kind of the idea with a discrete random variable is that you take something, it could be as simple as, looking at the genders of two babies born to a family, to a set of parents. Now, suppose that they are, fraternal twins, in which they are not identical. Now, we could let our random variable count the number of girls between those two babies. And X, as is usually the case, is going to be that random variable. Now, what we do in looking at the distribution is we go down and list all the possible values that X could be. X being the number of girls. X could be 0 or 1 or 2. Now, how do we get that probability? Well, we can go out and collect data. For example, we can go out and randomly sample a whole bunch of families with two babies. Two children who are not identical twins. And we can ask them, how many girls do you have between your two children? And suppose that we get this data here. Suppose that 27 families said that they had 0 girls, 2 boys. 56 families said that they had 1 boy and 1 girl. And 17 families said that they had 2 girls. And then you could add up these frequencies, divide by the grand total, and get the, you can calculate the average. And I'm going to show you how to calculate X bar here. But it's group data, excuse me. And I'll also show you how to calculate the standard deviation. Again, this is group data. So if you understand how we did the calculation for x bar and s from a previous chapter, then you understand how to do it for this one right here. But this is really not what we're talking about there. We've already talked about how to do this, though. Now, theoretically, if there's an equal chance of having a boy versus a girl, then the probability of having 0 girls and 1 boy is going to be 1/2 times 1/2, because there's a 1/2 chance for each baby of there being a girl or a boy. So the probability of having 0 girls means that is going to be the same as the probability for having 2 boys. 1/2 times 1/2, which is 1/4. Probability of having 1 girl, well, that event of having 1 girl is broken down to having either a boy and then a girl, or a girl and then a boy. Now, there's 4 total possible outcomes, and 2 of those 4 result in there being 1 girl, so there's a 1/2 chance, 0.5, of having 1 girl. And finally, probability of having 2 girls out of 2 children is 0.25. We've already seen how to do this calculation from chapter 4 for these probabilities. Now we put these together to create this probability distribution where x is our random variable. It could take on the value of 0, 1, and 2. And for each one of those values, you have a particular probability. Notice these probabilities add up to 1. And here's the mean, and here's the standard deviation. I will show you how to calculate this mean and the standard deviation. Excuse me, having a little bit of gastric problems. Doing just fine. All right, so this is what we're talking about here in chapter 5, is how to take a probability distribution and do certain calculations. For example, how to calculate probability of certain events. Also, how to calculate the mean of that distribution. How to calculate the standard deviation of that same distribution. Okay, so here we go. Moving along to section 5.2, where we're going to get into the weeds here. We're talking about taking a probability distribution and doing some calculations with it. And in particular, we're going to be taking a look at what it means for some sort of outcome to be unusual. Well, I think we already know what that means. That means that it's unlikely to have happened. But first, let's define random variable. Random variable is nothing more than a variable, hence the name random variable, where you have some letter of the alphabet. Typically it's X, could be Y, could be Z, in which you input a single numerical value. Could be the number of girls out of so many children, or it could be the number of heads out of so many coin flips, or the number of ones out of so many rolls of the die. X is going to be some number, and for each different value of X, there is going to be a corresponding probability. The probability distribution is what gives that probability spread for those different values of X. Could be in the form of a table, of a chart, of a formula. 2 different flavors, discrete versus continuous. We're going to focus on discrete right now, continuous later. Discrete means that your random variable will take on only discrete values. For example, the number of ones out of 20 coin flips. Out of 20 rolls of the die. Either X is 0 or 1 or 2 or 3 or 4 or 5, ... all the way up to 20. Does it make sense for X to be, say, 1.5 or square root of 2 or 1.414? Discrete's going to happen when your random variable can only take on maybe integer values, whole number values, etc. But not over a spectrum. For example, the continuous random variable would be exemplified by, say, in the measure of the length of a snake, or someone's height, or weight, or something's weight. I already said that. But the point is that each of those measurements could take on any real number value on the real number line. Okay? Along a continuous scale. Okay? Now, whether you have a discrete or continuous distribution, there are some things that are going to hold. First of all, we know that the total probability of any sample space is always equal to 1. So the sum of all the probabilities, meaning the sum of the probabilities for all the values of x's, must add up to 1. And then also is that the probability for any event, for any value of x, is always between 0 and 1. Okay? Here's an example of a probability distribution. It's in the form of a histogram in which we have a vertical bar chart. Now, the setup for this example is that suppose that we were to go back and take a look at all the 12-person jurors in court cases and trials in some part of the country, like Texas, over the last, say, 100 years. And for each jury, our random variable is going to count the number of Mexican Americans. As you can imagine, there have been thousands of trials, so therefore we can get a pretty good distribution. And this is the shape. It's going to be left skewed. Okay? So from this, we can get a probability distribution from all that data. Look on the vertical axis, we have probability. This shows that the most likely number of Mexican Americans on a jury is somewhere in the neighborhood of is 10 with a probability of 0.3. The next highest likelihood number of juries is 9, or jurors who are Mexican American is 9, with a probability of about a quarter, 0.24, something like that, followed by 11. Whatever number of Mexican Americans in a jury, that probability is estimated just by taking the height of the bar over the respective number and then looking at the corresponding point on the vertical axis. Look at the height of the bar. That's about 0.14, for example, for 8 Mexican Americans on a jury of size 12. And if I were to take a look at and calculate the area of all of these vertical bars, those areas would add up to 1. Because of this fact that the sum of the probabilities for any sample space, and thus for any probability distribution, must be equal to 1. Okay? So there's an example of a probability distribution in the form of a graph. Could be in a chart, table, formula. However you get your distribution, here are some calculations. First of all, the mean of the distribution is going to be where you take each possible value of x times its corresponding probability, and then you add up those products. So if you want to calculate the mean number of Mexican Americans on a jury, well, then what you'll do is you'll take each possible value, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, take each possible number times its probability. So you'd have 0 times 0 plus 1 times 0 plus 2 times 0 plus 3 times 0 plus 4 times, I don't know, 0.01 plus 5 times 0.015 or whatever plus 6 times 0.02 or something plus 7 times 0.05 or whatever plus 8 times 0.14 plus 9 times 0.24 or whatever, and plus 10 times 0.3 plus 11 times 0.21 or whatever that height is, plus 12 times 0.06 or whatever that height is. So you just take each numerical value of the random variable times its local or a corresponding probability. Add them all up. That's what this means. Calculate the variance. You take each possible value for x minus the mean squared times the corresponding value for x. Add them all up. Now, if you were to manipulate this formula for variance, mathematically it works out to be equivalent to this guy right here. If you're interested, I could show you the details. Different way for calculating the variance. And remember, the square root of the variance is equal to the standard deviation. So if you have a probability distribution, you want to calculate the mean, here's the formula for the mean, here's the formula for the standard deviation. Expected value of a probability distribution is, as we've seen maybe in a previous discussion, you take each possible value for x times its probability. But hold on, isn't that the same thing as this one right here for the mean? Yes, it is. The mean of a probability distribution is the same thing as the expected value. The letter E means expected value in relation to a probability distribution. So here's an example here. Suppose that we've got, this distribution for the number of girls in a family of 2 children. Probability of having 0 girls out of 2 children is 0.25. Probability of there being 1 girl out of 2 children is 0.5. Probability of 2 girls out of 2 children, 0.25. Meaning, if you were to randomly select a family with 2 children, there's probability of 0.25 that there's 0 girls, probability of 0.5 there's 1 girl, probability of 0.25 that there's 2 girls. Now, we can calculate the mean, variance, and standard deviation. So first of all, you're going to want to calculate x times p of x. So you take each possible value of x times its probability. 0 times 0.25 is 0. 1 times 0.5 is 0.5. 2 times 0.25 is 0.5. Add up those x times probability of x's, you get 1. Also, take each value of x minus the mean. By the way, what's the mean? 0 times 0.25 plus 1 times 0.5 plus 2 times 0.25, and that works out to 1. So if you were to take each possible value of x minus 1, 0 minus 1 is negative 1. Squared is 1. 1 times the probability of 1 is 0.25. And likewise for these other two. And you add them up, you get 0.5. So the variance is going to be 0.5. So the mean was 1, variance was 0.5. Standard deviation of that distribution was the square root of the variance. Square root of 0.5 is approximately 0.707. Now remember the range rule of thumb that says that, if you were to take the range divided by 4, that would be approximately equal to 1 standard deviation of that distribution. Turn that around, that says that, 95% or so of the distribution should fall within 2 standard deviations of the mean. So that means any observation, any value that is either above 2 standard deviations over the mean or 2 standard deviations less than the mean, meaning if you have an observation or a value that's above this mu plus 2 sigma greater than 2 standard deviations above the mean or 2 standard deviations below the mean, if your value is below that, any observations that's outside this range will be labeled as unusual. So going back to our little cheesy example here, for our probability distribution for the number of girls out of 2 children, we saw that the mean was 1.0, standard deviation of 0.7. So if you were to take mu plus 2 sigma, that would be 1 plus 2 times 0.7, meaning 1 plus 1.14, or 1.4. So 1 plus 1.4 is 2.4. And also mu minus 2 sigma, that'd be 1 minus 2 times 0.7. That's 1 minus 1.4, which is negative 0.4. So if it were possible for us to have, less than 0 girls or more than 2 girls, any observation that's greater than 2.4 or less than negative 0.4 would be considered unusual. Okay? Now, where this is really going to be useful in helping us make a decision is this rare event rule for inferential statistics. Let's go ahead and read this together. If under a given assumption, such as the assumption that a coin is fair, suppose that you have a particular observed event. For example, you flip a coin. And in particular, you flip a coin, say, 1,000 times. And you count, a certain number of heads. For example, 992 heads. Now, if it's a fair coin, we would expect to have approximately 500 heads out of 1,000 coin flips, because there's would be a 50-50 chance of any particular coin flip coming up heads. And when we get to binomial probability, I can show you how to calculate this, but the probability of getting 992 heads or more out of 1,000 coin tosses, that probability actually works out to be rather small, much less than 0.05. Because of the fact that under this assumption that we have a fair coin, that the probability of getting this number of heads out of 1,000 coin tosses, the probability of it being so small probably indicates that the assumption that we have a fair coin is wrong. Okay? As we shall see, now it could have been just our dumb luck that we do have a fair coin, but that we just happen to flip 992 heads out of 1,000 coin tosses. We don't know, but it's very unlikely to have happened by chance alone. So let's make sure that we understand this. If you perform a trial, as in a coin flip, and you do it a certain number of times, like n number of times, and you count the number of heads or whatever you consider to be a success, and you want to try to decide, is it unlikely to have that number of heads or more if you think that you have an unusually high number of those successes, well, all you need to do is calculate the probability of getting that number of successes or more to get a value of x at least as extreme as you did under the assumption. And if that probability of having at least x number or more is less than or equal to 5, or 0.05, I mean, or x or fewer on the low end, if you wanted to decide if you had an unusually low number of tails out of so many coin flips, you calculate the probability of getting that number of heads or fewer. And if that probability is less than or equal to 0.05, either in this case or this case, then you will decide that, you know what, it's unlikely that your assumption, your hypothesis, is right, because we got an unusual high or an unusually low number of successes under that assumption. The key number here, the key probability is 0.05. If the probability of some event is less than or equal to 0.05, that means it's an unusual outcome. Okay? So that's it for today. We will continue this discussion tomorrow. Probability distributions. All right. Have a good day, and I'll see you next time.